Okay, everyone. So I think we may begin now. Again, a very good morning to all of you. Selamat pagi semua. Apa khabar pagi ni? Semua sihat ke? Have you all took your breakfast? Sudah makan semua? Okay, so thank you for being here. So as I mentioned before, so we continue with our discussion on the next content standard on 6.3 today. It is image formation by lenses. Okay, before this, we have finished with 6.2, total internal reflection. So have you tried to do the exercises in your workbook, students? Eliana, Eric, Yanxin, we have Xiu Jing now, Hui Xin, Chiu Yi, Qin Xiang, and Yi Xian, Sun Xiang, Yu Qian, this one, Jin Pei, Po Yu Hui, Wan Jia, Yi Ting, Man Ting, Xin, Wei Yuan Han, and Hong Zhe. Okay, have you tried to do the exercises on your workbook on total internal reflection? I didn't share to you the answer yet, right? Okay, so later on, I will share the answer to you. So I hope you can try to do the exercises on total internal reflection in your workbook on page, started from page 175 until 178. Okay, nanti cikgu kongsi jawapan dia after this lesson ended. Okay, so without further ado, let us begin our discussion on 6.3, image formation by lenses. Okay, good morning for those who just been here. We are just about to start. Okay, so this is the third content standard, in chapter 6, 6.3, image formation on lenses. Okay, students, in this content standard, altogether there are 4 learning standard you must master very well. So if you open your workbook, if you open your textbook, 6.3 will be started from page 251, 251 until 258. And if you go through your textbook, there are a few QR codes which you can scan, okay? And you can watch a short video or some simulation on image formation by these lenses. Okay, so the first learning standard, let us begin with 6.3.1. It is to identify convex lenses as converging lens and concave lenses as a diverging lens. So why do convex lens are called as converging lens? And why does concave lens are called as diverging lens? So we are going to discover that today. So before that, you have to know what is lens, students. So what is lens? It is a piece of transparent material, okay, made from some either from glass, perspex, or plastics. And lenses, it must has 2 surfaces with at least one of the surface must be a curve. Okay, so the difference between lenses and other transparent material, not all transparent material we can call as lens. Okay, lens must have 2 surface where at least one of the surface is curved. For example, if you look at these 2 glass blocks, okay, the first glass block, it has 2 surface. So where is the first surface? This is the first surface on the left, and this is the second surface on the right. And you can see the surface on the right has a curved shape. So we call it as a lens. The surface here is a plane. Okay, it's a straight surface. Yeah, morning, Ong Cheng. While the second glass block down here, why it does not call as lens, students? So you can see it also has 2 surfaces, the first surface, the second surface, or this is the first surface if you're looking from this side. Okay, the first surface, the second surface, but it does not have any curved surface. Okay, so since it does not have any curved surface, so we didn't call it as a lens. Okay, even though they are both glass block. Okay, transparent. Refraction of light can be occur, but this second glass block is not called as lens again because it does not have a curved surface. So I hope you know what is lens. It is a transparent material which has 2 surfaces with at least one curved surface. Okay, good morning. Okay, then okay, you learned already refraction. Okay, refraction is a bending of light. when a light passes through a medium of different optical density. Why the light bending? Because the velocity or the speed changes, okay, when passed through two medium of different optical density. So in lenses, we apply refraction of light. Okay. All right, students. So these are the two types of lenses which you must know very well. Generally, we have convex and concave lens. And these are a few examples of convex lens. Okay, if you look, the first one is called as biconvex. Okay, it has curved shape in both surface. Okay, and the second type is called as plano-convex. Plano-convex, it has one curved surface. The other surface is a plane shape. So it is called as plano-convex. And the third shape, this is called as convex concave meniscus. Okay, convex concave meniscus. And what is the similarity between all these three convex lenses? You can see that they are thicker at the center. Okay, sorry. So you can see this is the center. So they are thicker at the center. Okay, compared to the edges. Okay, so this is convex lens. Okay, while this one is concave lens, example of convex lens, we have biconcave. Okay, bi mean both surface are curve shape. Okay, and the shape is curved inwards. Okay, for convex, the shape is curved outwards. That's why it is thicker at the center. And this one, it is curved inwards. So that's why at the center, it is thinner. Okay, if you look at the center is the thinnest part of the concave lenses. Okay, this one is plano concave. It has one curved surface. The other surface is a plane shape. Okay, and the third one is called as convexo concave. All right. So the similarity thinner at the center. So I hope you, when you are given the diagram of these lenses, so I hope you can identify which one is convex and which one is concave lens. So the keyword is here. Just look at the center. Thicker is convex. When the center is thinner, so it is concave lenses. Okay. Okay, then this one, students, why convex lens are called as converging lens? Okay, this is because if you look from this short animation, when the light passes through these lenses, it is refracted, okay, and it is focused on a point here. See, all these five parallel light, 1, 2, 3, 4, 5. You see all these five light. After passing through these lenses, it is focused at the point, mean it is converged. Converged mean it focus on one point, okay? And this point is called as the focal point of the lenses. Okay, meanwhile, for concave lens, if you look at this animation, again, all these five parallel light, after passing through the lens, you can see that it diverges out, okay? It diverges. So we say it is diverging lens. All right. So the points here you can highlight or you can fill up the blank spaces in your module. The light ray pass, the light ray which is parallel refracted inwards. Inwards mean it refracted to a point, converge. Okay, refracted inwards and converge on a point. So this is the point of where all the light converge at. Okay, and it is called as the focal length, and the focal length is called as real. Okay, and this is called this small f is called as the focal length. Focal length, later we will look at the next point, what is meant by focal point, what is meant by focal length. Okay, so for concave lens, again, the light ray which is parallel refracted outwards. So you can see it refract outwards in this direction, and it is diverge. Okay, diverge on a point F, which is passing through the lens. So for concave lens, students, the focal point is in front of the lens. Okay, this is another difference between convex and concave. For concave, okay, for concave lens, the focal point is in front of the lens, while for convex lens, the focal point is behind, okay, behind the lens. Okay, so are you doing good so far? Can you follow me? Okay, so this activity 1, you can find in your textbook. It is written there as activity 6.7 on page 251. Okay, 251. This is an activity to show convex lens as a converging lens and concave lens as a diverging lens. Okay, so if you have lenses at home, you can try this. Okay, you can try this activity at home. Okay, so these are the procedure of conducting this activity. So the instruction you can read from number 1. We started with the setup. Okay, we set up the apparatus as shown here. So we place our cylindrical convex lens in front of a ray box. Okay, you can see there are 3 slit plate here to create parallel lights. Okay, projecting to the convex lens. And this is the white paper where we can trace the refracted light, okay, after passing through these lenses. Okay, then this is how we conduct. We set up the apparatus and then we trace the shape of the convex lens on the white paper. So we direct the 3 parallel light from the ray box towards the convex lens, and then later we can observe, okay, the beam of light after passing through the lens. And we can make 2 marks on each part of light before and after passing through the lens. After that, we remove the convex lens and draw the ray diagram. So class, when we draw the ray diagram, this is what you are going to get. Okay, this is the convex lens we place now. And then later we replace, okay, if you read procedure number 6, okay, we repeat step 2 until 4 by replacing the convex lens with the concave lens. Okay, so this is the find out from this activity. So when we are using convex lens, this is the ray diagram you are going to get. Okay, the light ray at the center passes through the convex lens here without refracted. Same things goes to the concave lens. Okay, the light at the center passes through the convex lens. Undeviated means without being refracted. Okay, mean it continue travel in a straight line. Okay, this one, the light at the center, at the principal axis. Okay, same things goes for the concave lens. While the other light converge at a point. Okay, for convex lens, you can see light number 1, number 2, number 4, and number 5, they are converged to a point. Okay, while for concave lens, light number 1, number 2, number 4, and number 5, they are diverged from the focal point in front of the lenses. Okay, so here we understand that convex lens converge light ray, concave lens diverge light rays. All right. Okay, so we have done with the first part. Okay, to understand convex lens, why it is called as a converging lens, because it converges light to a point when the light passing through the lens. And why concave lens is called as a diverging lens, it is because it diverges light rays after passing through the lens. Okay, so now we go to the second part. This is to understand the optical terms and the explanation for each. Okay, this one you can find in your textbook on page 252, 252. There are table 6.5. Okay, optical terms related to lenses. Okay, students. So they are altogether, they are 7 optical terms which you have to know very well. Okay. So the first one is called as the optical center. So can you please open your workbook on page 181? Boleh ambil buku kerja kamu, the purple book. Okay, you can turn to page 181. 181. 181. Okay. So you can see there is a table there. Table of the optical terms, terminology, the symbol, and the definition. Okay. So if you look at the first terms, optical center given with the symbol O. So you can write the symbol there in your workbook. Okay, so write the symbol there, O, optical center, capital O. So what is the optical center, student? Optical center is a point at the center of the lens. So where is the center? This is, okay, this is the optical center. Okay. And light ray passing through the optical center are not refracted. Okay, for example, if there is a light passing through the center in this way, so it will continue travel in a straight line. Okay, same goes to a concave lenses. Okay, if there is a light passing through the optical center, for example, so it will continue travel in a straight line without being refracted. Okay, so second we have principal axis. Okay, principal axis is the center line, this one. Okay, this is the principal axis. It is a straight line through the optical center of a lens and the center of curvature of both surface of lenses. All right. Okay, then this one is the principal axis for concave lens. Okay, then we have the third terms, focal point. So what is focal point? Focal point is a point located at the principal axis of a lens. And for convex lens, okay, for convex lens, you can check the light ray, which is parallel to the principal axis, will converge at this point. Okay, converge at this point after passing through the lens. Okay, for example, this is the light parallel to the principal axis. So after passing through the lens, it is converged to the focal point. So these are the focal point for convex lens. Same goes to the light here. The light here is parallel to the principal axis. After passing through the convex lens, it will be focused or converge at the focal point. Okay. Meanwhile, for concave lens, students, where is the focal point? As I mentioned earlier, for concave lens, the focal point is at the front. Okay. So what happened to the light ray after passing through a concave lens? So a light ray which is parallel to the principal axis will be diverged. Okay, diverge, and as it is appear from the focal point in front. Okay, as written here. The principal axis appear to diverge from the point after passing through. The same goes to the light here. Okay, this is a light ray parallel to the principal axis. So after passing through a concave lens, it diverges out. Okay, and as if it is diverged from the focal point at the front. Okay, so I hope you know where is the position of the focal point. For convex, it is behind the lens, and for concave, it is in front of the lens. Okay. Okay, talking about in front and behind students. Okay, normally we are placing our object. Okay, this is our lens. Okay, actually, normally the left side. Okay, the left side of the lens is called as the front. Okay, at the front part of the lens. This one also the same. The left side of the lens is normally called as the front part, where we place our object at. Okay, and the area at the right side is called as the area behind the lens. Okay, this is for convex and this is also for concave lens. So I hope after this, nobody will ask which one is the front, which one is behind. Okay, and this is fixed. So the front part is the left side. Okay, the right side is the back part of the lenses. Okay. Okay, then the fourth terms is the focal length. So this is focal length. The symbol is small f. Okay, this is the focal length for concave lens as well. So what is focal length, students? It is a distance. Okay, the distance between the focal point f and the optical center. So this is our focal point. This is the optical center. So the distance is called as focal length. Okay. And for concave lens is also the same. This is the optical center and this is the focal point. So the distance between these 2 points is called as focal length. Okay. While the fifth term is object distance. Okay, object distance with the symbol small u. Okay, object distance. Object distance is defined as the distance between the object and the optical center. Okay, let's say we place an object here. Okay, we place an object here. So the distance of this object at the optical center is called as U. Okay, same goes to the concave lens. Let's say I place the object here. So the distance between this object and the optical center is called as object distance. Okay. And number 6, we have image distance with the symbol of small v. Okay, so what is image distance? It is a distance between the image and the optical center. Okay, image and optical center. Okay, let's say the image formed here. Okay, let's say for this convex lens, the image finally formed here. So the distance from the image to the optical center is called as V. Okay, same goes to this concave lens. Let's say the image appear here. Okay, so this is V, image distance and the optical center. Okay, and the last terms is axis of lens. Okay, what is axis of lens? It is a straight line through the optical center and perpendicular to the principal axis. Okay, this one. Okay, the dotted line here is called as axis of lens. This is the axis of lens for convex lens. A straight line through the optical center. And so this is the optical center, a straight line, and it is perpendicular to the principal axis. Okay, perpendicular to principal axis. Straight line through optical center and perpendicular to the principal axis. So I hope you can get yourself familiar with all these terms we are using in understanding lenses. Okay, do you have a question so far? Any question? No? So I guess everybody is doing fine with the first part, nothing much yet, only to understand what is concave, what is convex lens, and the optical terms. Okay, Sinwei, thank you for responding. Okay, now let's move to the second learning standard, student. This is to estimate focal length for convex lens by using a distant object. Okay, this is the second activity in your textbook on page 253. Okay, how to estimate focal length for convex lens. Okay, so this is the screen. This is the slide show to you how we can estimate focal length of convex lens. 4 steps. It involves 4 simple steps only. The first step, what we do, as shown in this diagram, we place a convex lens directed towards a distant object. Okay, for example, we place our lens here aside from this window. Okay. Second, we place the screen behind. We place the screen here, the white screen, and we adjust the position of the screen until you can see a sharp image appear on the screen. For example, there is a house up there, right? So if we adjust the screen until you can see a sharp house image appear on the screen. For example, it's shown here. So if you zoom, okay, let's zoom at this part. Okay, this one. So when you adjust the screen, it is not 10 centimeter from the lenses. The image is quite blurry, right? The image is not clear, it's quite blurry, so we have to adjust. Either we bring it closer or further. So here when we bring closer, now it is 5 centimeter from the lens, the image is more sharp. Okay, it is more clear. So then we stop adjusting. Okay, so we place our screen 5 centimeter from lenses. Okay, this is how we do the adjustment on the position on the screen until you are satisfied with the sharp image produced on it. Okay, so the sharp image on the screen is called as a real image. Okay, students. So what is a real image? Real image is an image which can be formed on the screen. Okay, that is called as a real image. Another one, we have virtual image. Okay, virtual image means the image cannot be formed on the screen. Okay. Okay, then this one, number 4, the distance between the optical center and the screen. This is what we call as the focal length of the convex lenses. Okay, this one, the distance. Okay, distance between the optical center. This is the optical center. We mark it here. And then the screen. So this is what we call as the focal length, which means when there is a distant ray which travel parallel to the light ray, so what happen? It will be focused on this point. Okay. Macam inilah cikgu lukis. Okay, it will be focused on this point. So this is the focal point. So this is the focal length. Okay. How to know parallel? Okay, a light travel from further distance, it must be parallel, Nicholas. Okay, if the object is very far away, so the light is travel in a parallel way. So we call the object is at infinity because we don't know the exact distance. Okay. Okay, then next. Okay, this is the second activity. Okay, this is to observe real image and estimate focal length. Okay, this is the same activity as before. Sama juga. So this is all the apparatus you need: convex lens, meter rule, lens holder, and widescreen. Right? This is the setup of apparatus. Okay, we place a convex lens on a lens holder and position it towards an open window. Place the widescreen behind the lens. And as before, we adjust the position of our screen until we get a sharp image. Okay. So the image you look at the screen is called as a real image. Okay. Then you can measure the focal length as I discussed with you earlier. Okay. And there is a one question here, why this activity above is not suitable to be used to estimate the focal length of a concave lens. Okay. So if we are using concave lens, so what is going to happen? Okay, as it written here, the object must be far enough for parallel a light ray from the object to be converged at the focal point. Okay, so Nicholas, this is actually what you are asking just now. Okay, so a light coming from a very far away object, it is travel in a parallel way. Okay. If the object is not far enough, they may not have parallel light ray for the formation of image at the focal point. Therefore, the distance of the concave lens from the screen is not exactly equal to the focal length. Okay, if you are using concave lens, the distance you are going to get will not be accurate or will not be the exact focal length. Because as we discussed earlier, students, for concave lens, okay, let's say this is the light ray traveling through the lenses from a very far away distance. Okay, for concave, it is going to be diverged, right? Okay, it is going to be diverged in this way, and this is where the focal point is at. Okay, and this is the focal length. Okay, so this is the focal length. And let's say this is your window. Okay, let's say this is your window. Okay, so this is the window, the light coming from your window. Okay, enter parallel to the concave lens. So the problem we are going to have with the concave lens, it is not going to give you an accurate distance for focal length because this one, okay, they may not have parallel for the formation of image here. It is very difficult. Okay, it is very difficult to get compared to if we are using convex lens. Okay, even though you adjust the screen, it is very difficult to get the real image on the screen. Okay, so that's why this activity is not available or is not reliable to be applied in order to determine the focal length of a convex lens. It only can be applied on convex, okay, not for concave. All right. Okay, now this one, so it's 6.2.3, 6.3.2, nothing much at all. Okay, this one is the most important part. Okay, 6.3.3 to determine the position and features of image formed by convex lens. Okay, because, okay, another thing is why for concave lens, okay, it is very difficult for us to estimate because for concave lens, later we will learn in 6.3.3, the image formed for concave lens is a virtual image. Virtual image means we cannot see the image formed on the screen. And that's why it is very difficult for you to see where is the focal length. Because when you adjust, even though you adjust the screen to the front and to the back, the image won't be appear on the screen because it is called as a virtual image. So there is no way we are going to determine the focal length. Okay. Okay, now 6.3.3, this is to determine the position and characteristic of features of image formed by both lenses. Okay, this one you can find in your textbook on page 254. Okay, students, we are going to look at the general ray diagram first. Okay, so number one, if you look at this point, the position and features of characteristic. Features is a characteristic, okay, of image formed by convex lens. Later, you will learn there are three characteristics we can write for image formed for both lenses. Number one, either the image is real or virtual. Okay. Second, either the image is inverted or upright. And number three, the size of the image. Either the image is magnified, diminished, diminished means smaller than the object, or it has the same size with the object. So these are the three general characteristics of features of the image formed by both lenses. Okay, and in order to determine this characteristic, there are rules which you have to obey in order to construct the ray diagram. So what are the rules? Actually, there are three rules. Okay, three rules. The first rule, okay, number one, the first rule, a ray which is passed through the optical center travel in a straight line. So this is what I mentioned earlier. Okay, if you look for both convex and concave, the light that travel through the optical center, it won't be refracted, mean it will continue travel in a straight line after passing through the lens. This one also, it continue travel in a straight line after passing through the convex lens. So that is the first rule. Okay. Second rule, okay, second rule for convex lens, a ray parallel to the principal axis. So this is the ray parallel to the principal axis. This is our principal axis. Okay. So what happened to this ray? It will be converged to the focal point. Okay. While for concave lens, a ray parallel to the principal axis will be diverged. Okay, diverged from the focal point at the front. Okay, so this one converge to focal point. For concave, it is diverged from the focal point. Okay, that is the second rule. And the third rule, students, a ray that passing through the focal point as shown here. So this is the ray passing through the focal point of the concave lens. So what will happen? It will be refract in a straight line parallel to the principal axis. Okay, same goes to concave lens. A ray pass through the focal point here, so it will refract parallel to the principal axis. Okay, so number 2 and number 3 is the opposite. Okay, if you notice rule number 2 and rule number 3, they are in the opposite way. Okay, why the light ray no draw in parallel to the normal line? Which one, Nicholas? If mana datang dari sini, if the light coming from here, then there is no refraction. If the light coming from here, so it will continue travel in a straight line in a normal light. Okay, no refraction occur. Same goes to this. Okay, ini kita tak panggil normal line. This is we call as a axis, lens axis. Okay, for lens, this is not the normal line. This is the lens axis. Okay, if you look at the table just now, ini lens axis. Lens axis is a line, straight line to the optical center and perpendicular to the principal axis. We didn't call it as normal line here in lenses. Okay. Okay, next. Okay, so you know the three rules already, how to draw the ray diagram. Okay, so now this is the image position and characteristic of image formed by convex lens. Okay, students, if you look at this simple simulation here, for convex lens, the characteristic of the image varies depending on the position of the object. Okay, for example, you can see the black one ini is the object. Okay, the black arrow is our object and the blue arrow is our image. And you can see that if we adjust the position of the object, either we bring it closer or further to the lenses, a different characteristic of image will be appear. You boleh tengok sini. Okay, this is object size and this is how the image is seen. Okay. So from here, for convex lens, the characteristic and position of image, okay, it can be formed at the same side as the object. Mean we place the object in front, the image can form in front of the lenses, or it can form behind the lenses, okay, at the opposite side of the object. Okay, and the characteristic, it can be virtual or real, it can be upright or inverted, and the size, it can be diminished, same size, or magnified. So the image and characteristic varies depending on where is the object distance or where is the position of the object. Okay. So to go more detail, you can see this table. Okay, first, can you look again in your workbook, page 141? Okay, please go to your workbook 141. Okay, look at activity B. Okay, just now we have completed a table on the symbol of the optical terms. So I hope you have completed with all the symbol. Optical center, optical center, the symbol is O. Principal axis, no symbol. Lens axis, also no symbol. Focal point, the symbol is capital F. Okay, focal length, the symbol is small f. Object distance, the symbol is small u. Image distance, the symbol is v. Okay, now for B, students, activity B on page 181. Okay, complete the diagram for image characteristic statement. Okay, so just now for characteristic of image, I tell you there are three pairs of characteristics. So the first one, what to write there? What or virtual? So you write there, it is real. You write there real. So it is real or virtual. Okay. And then second characteristic, inverted or upright. So you write there upright. And then the third characteristic, it can be magnified or diminished or same size with object. So you can write there diminished and then same size as object. As stated here, this is how to spell diminish. Okay, diminish means smaller than the object. Okay, then down there, okay, you can see they are real image and virtual image. So what is real image, student? Real image is the image that can be formed on the screen. Okay, you write that. Right there, that can be formed on screen. Okay, real image. Okay, we are discussing it now, Nicholas, real image and virtual image. Okay. Okay, and then for virtual image is the image that cannot be formed on the screen. Okay, cannot be formed on the screen. Okay. Visual means ridiculous. Okay, if you look at the mirror, okay, if you have a mirror aside you just now, okay, if you look your image at the mirror, if you look into the mirror, your image is not formed on the surface of the mirror, it formed inside. Okay, it formed inside. So that is what we call visual. It does not form at the surface of the mirror, but it formed inside, or we say form uh, in the mirror. That is called virtual. Okay. Okay, then, okay, next students, okay, this one is the for convex lens students, there are 6 possible places where we can place the object is at. Ada 6 tempat you boleh letak object. Okay, the first one, the object is very far away, so we call it as infinity. Okay, U is infinity, U is object distance, infinity means the object is very far away. So this is the light travel. Okay, this is the light travel as shown in your textbook on page 256. Okay, so if you follow the 3 rules just now, okay, so for this one, the red line here, the light passing through the optical center, so it does not refract. Continue travel in a straight line. Okay, and then for the second line, okay, this is the second rule. Okay, the line passing through the focal point, and this is the third rule. Okay, this is the third rule. The line passing through the focal point, it is refract in a straight line. So this is the intersecting point between these 2 lines. So this is where the image will form at. So we draw our image from the principal axis to the intersecting point. So you will find out the image will be inverted, terbalik. Okay. And this is the object distance. Okay, the image distance. So here the image is formed exactly at the focal point. Okay, and the characteristic is, okay, to know the characteristic either real or virtual. Okay, now you look, okay, the object is here. The object is on the left side. Okay, mean on the front part of the lenses. But now the image formed at the opposite side. Okay, opposite. So opposite is real. Okay, when it formed in the opposite side, we call the image as real. Okay, this one. Form at this side is real. If formed at the same side with the object, so we call it as a virtual image. Okay, and then inverted or upright, you just have to look. If the image is formed below the principal axis, so it is inverted. Okay, and then the size is diminished. Okay, smaller than the actual object, right? And this is the application. It is applied in the objective lens of a telescope. Okay, telescope is used to observe a very far away object like the star, the planet, and everything up there. So object distance is infinity. All right, anybody raising a hand? Okay, then this is the second position. Okay, now we place the object greater than 2f. Okay, this is, okay, this is the object distance now, u. Okay, u greater than 2f. Okay, u diminish means smaller. Okay, smaller than the real size of the image. Okay, diminish means the size of the image is smaller than the size of the object. Okay, if magnified means the size of the image is bigger than the size of the object. Okay, okay, then, okay, this is our object, Nicholas. Okay, for the second position. Okay, this one. Okay, the black arrow is our object. We place it now at the position greater than 2f. Okay, so this one we apply. This is rule number Number 1, number 2, or number 3, students? The green light. The green arrow here. The green one, this one is rule number. This is rule number 2, right? Okay, rule number 2. So a line parallel to the principal axis will be converged at the focal point. Okay, then we draw the second line. Okay, the red line here applies rule number 1. Okay, rule number 1. Okay, and this is the intersecting point. So the purple arrow is our image. This is our object. Okay, this is our object. This is our image. Okay, now object is on the left. Image is on the right. Again, it is formed at the opposite side. So we call our image as real. Okay, real. And then upright or inverted. So it is inverted. Okay, and it is diminished. Diminished, you can see the image is smaller. Okay, yes, below inverted, right is real, lower than 2f. Lower than 2f, this is greater than 2f. Okay, so you can see the size of the image is smaller than the size of the object, so we say it as diminished. So where to apply this position on the lens of a camera? Okay. Okay, next, students. Okay, object distance. Now U is exactly at 2f. So this is our object, O our object. So this is the object distance now. Okay, U is equal to 2f. Okay, so we can apply the first rule. Okay, this is the first rule. The red line is the first rule. And this is the second rule. Okay, the second rule passing to F. So this is the intersecting point. So where our image appear at or form at. And now the object distance is 2f. Okay, V is 2f. Again, it is opposite, so it is real. Form below the principal axis, so it is inverted. And then the size, you can see now it has the exact size as the object. So we say it has the same size as object. So application, we apply this in photostating machine. Okay. Okay, and this is the fourth position. Now U we bring, it is in between F and 2F. Okay, the object distance is in between F and 2F. So again, you can apply rule 1, and then this one rule number 2. So this is the intersecting point. Again, opposite, inverted, but now you can see the size is magnified. Okay, the image has a bigger size compared to the object. So we say it has been magnified. For application, you can find on objective lens on a microscope. All right. Okay. This is the fifth position. U is placed exactly at F, at the focal point. Okay, so for this one, we can apply rule number 1 and we apply rule number 2. Okay, for this case, you will find out there is no way these two lines is going to intersect. Mean these two lines will be parallel. So where is our image formed at? Okay, so for this case, our image is formed here, formed at the infinity, somewhere up there. Okay. So image is formed at the same side. So image also formed at the same side with the object. So we say it as a virtual image. And it is upright. Okay, since it is formed above the principal axis and the size has been magnified. Okay, this is applied on an eyepiece of a telescope. Okay, eyepiece of telescope. And the last position, we bring the object now very close to the lens. Okay, very close to the lens where U is less than F. Okay. So for this one, we can apply rule number 1, the red line, a light passing through the optical center, it is not going to be refracted, continue travel in a straight line. Okay, and then we can apply rule number 2. A light parallel to the principal axis will converge at the focal point. And for this case, you will find out the line will be intersect at this side. Okay, it is intersect at this side. So this is where the image is formed at. Okay, so it is now formed at the same side as the object. So form same side as the object. So we call the image as virtual. Okay, and it is formed above the principal axis. So it is upright. Okay, and it is magnified. Okay, yeah. Virtual because it is formed at the same side with the objects. Nicholas, object on the left, image also appear here on the left, here on the same side. So that's why it is virtual. Okay, the image is very far away up there. Okay. Okay, so class, that goes for convex lens. So again, the conclusion, you can see that the characteristic of image is depending on where is the position of the object. No intersecting point because it is a parallel line. You can see it is parallel line. Okay, so we took the image is formed at infinity. Okay, because we don't know where is the actual distance, so we call it as infinity. Okay, for case 5, no intersecting point. That's why it is formed at infinity. All right. Okay, now students, for concave lens. Okay, just now for convex lens, we understand the size characteristic of image, position of image is depending on the position, but it is different with concave lens. For concave lens, it is not depending. Okay, the characteristic of image is not depending on the position of the object, which is placed in front of the convex lens. Okay, as you can see in the simulation, okay, the black arrow ini is our object. Okay, you can see that, and the blue arrow is our image. And you can see here, even though we bring the object, okay, we change the position of the object, it always forms the same characteristic of image, where the image is always virtual, always upright, and always diminished. Okay, virtual, upright, and diminished. So for concave lens, very simple, one characteristic of image only for all position. Okay. So we place the object here. So the image always form at the same side as the object. So it is always virtual. Okay. And it is always formed above the principal axis. So upright. And the size always smaller than the object. So we say it is diminished. So for concave lens, very simple. It doesn't matter where we place the object at. The characteristic of image is always virtual, upright, and diminished. Okay. Okay, example. Okay, let's try to place the object into different position here for concave lens. This one you can find in your textbook, page 257. Okay, number 1, for the first ray diagram, we place our object, the green arrow is our object, we place it beyond 2F. Okay, this is U. Okay, U greater than 2F. Okay, so we draw the first rule. Okay, the first rule is the yellow line. Rule number 1, passing through the optical center, no refraction, continue travel in a straight line. And this one we apply rule number, this is rule number 2. Okay, rule number 2, a light parallel to the principal axis will be diverged from the focal point at the front. So this is the intersecting point where the image appear at. Okay. And this is the image distance. Okay, this is the image distance. Image distance is less than F. Okay, less than F, less than the focal length. B less than F. Okay, and this one, we bring now the object closer. We place it very close to the lens where U is less than F. Object distance less than the focal length. And again, we apply rule number 1. Remember, rule number 1, we draw a line with the optical center. So no refraction, continue travel in a straight line. Don't forget the arrow as well. Okay, whenever you draw the ray diagram, you cannot miss the arrow or it will consider as wrong. Okay, a ray diagram without an arrow is considered as wrong. And here is the second rule from the object. Okay, parallel to the principal axis to the lenses, so diverge from the focal point. So this is the intersecting point, our image appear here. So this is image distance. Again, V is always less than F. Okay, so visual, upright, and diminish. All right. And for concave lens, it is used to correct short-sightedness. Rabun jauh. Siapa yang rabun jauh itu actually you pakai lens ini. Okay, concave lenses. Okay, this one is the, just now we discussed about the theory. This one is the activity related to this. How to determine the characteristic of image. Okay, and this is all the apparatus required. We need a convex lens, concave lens, a ray bulb, transparent paper mark, with an arrow as an object. So this is, we draw an arrow here as our object, and inside is a ray bulb. Okay. That's so this activity is normally conducted in a dark room. Okay, inilah you can read the setup. Okay, you can read the instruction for convex lens. We set up the apparatus, place the convex lens, and make the object distance as 30 centimeter. Okay. Then adjust the position of the screen until a sharp image is formed. Okay, so if you look at this one, we started with U. This is U. We started with 30 centimeter. Okay, we measure with the ruler. And then we switch on the ray box. Okay, then the screen here, we adjust to the front and back until we get a sharp image. And then we label it as object image distance. Okay. Okay, then we can repeat this experiment with different object distance. Okay, now we repeat with 20, 15, and 8 centimeter. Okay, and for concave lens, we do the same. You just replace the lens with the concave, and then we started with object distance of 20, repeated with 15, and actually this one is 8 centimeter. Okay, so we repeat it with different object distance and see what is the characteristic of image form. Okay. Okay, so this is what we are going to find out from this activity. This is the result for the convex lens students. Okay, when the object distance is 30 cm, image distance when you measure will be at 15 cm. Okay. And when the object distance is at 20, image distance is also 20 cm. And when the object distance is 15, you will find the image distance is at 30 cm. Okay, and when we place the object very close to the lens, you will find the image distance will be at 40 cm. Okay, why negative sana? Negative shows real virtual image is formed. Okay, virtual image means it form on the same side. Okay, so this one you can fill up the characteristic for this position. Actually, this one related to the table I showed you just now, different position of object or convex lens. Okay, and this is the result for concave lens. Okay, when we place the object at 20 cm, this is where the image appear at the distance of 6.7 cm from the lenses. Okay, why negative? Negative sign shows here virtual image is produced. Okay, negative sign shows virtual image is produced. And the position is always less than the focal length for convex lens as shown in this simulation. All right. Okay, so this is the question that come out from the activity for determine the position and characteristic of image. Okay, the first one, the first question. State the position of convex lens which form real image and virtual image. So if you study this table just now, for convex lens, the real image are formed when the object is placed at a distance greater than the focal length. Okay, when you greater than F, it will form real image, okay, for convex lens. Okay, then when the object is placed at a distance smaller than the focal length. Okay, when U is placed less than F, it will form a visual image. Okay. And then number 2, what are the common characteristics for real image formed by convex lens? If you notice from the table, all real image are inverted. Okay, all real image formed by convex lens are also inverted. So this is the common characteristic. Okay, while you can find out the virtual image form is upright. Okay. So this is another thing you can hold to. When the image is real, it must be inverted. Okay. If it is virtual, it must be upright. Okay. Okay, then number 3, question number 3. What are the characteristics of image formed by concave lens? Remember, student, concave lens, it does not depend on the position of the object. Okay, wherever you place the object at, it is always formed an upright, virtual, and diminished image. Okay, for concave lens. Okay, so I hope you are clear with that. Okay, so now let us try to do these few exercises on the third learning standard. Okay, let us test your understanding. Okay, the first question, can you tell me which one is the correct answer? You are given diagram 7. It shows the boy with his image on a plane mirror. Okay, imagine you are standing in front of a plane mirror. So you will see your image inside the mirror at the same distance. You are standing at 1.2 meter. Your image also 1.2 meter away from the mirror. Okay, the question is, which pair is correct to produce real, magnified, and inverted image of a boy? So real, magnified, and inverted image. Baru saja kita bincang tadi. Which one? Convex or concave? And where is the position? Position of the ball means the position of the object. Let's say A or B. Okay, so to produce real, magnified, and inverted. So it must be convex or concave, students. So do you remember the characteristic for concave just now? So for this one, apa jawapan dia? This one we are using convex, and then the position is greater than F. Okay, greater than F. Okay, what about question number 2? Okay, question number 2. Where should an object be placed in front of a convex lens? So you're given a convex lens with a focal length of F so that it can act as a magnifying glass. Okay, magnifying glass. Okay, which one? Okay, magnifying glass. You know magnifying glass? Normally when you use magnifying glass, where we place the object as? Okay, very close or very far away from the glass? Magnifying glass, student, we place very close to the magnifying glass, right? So we say less than F. Okay, the object distance is less than F. So it will produce a bigger image, virtual, upright, and magnified. Okay, how about the third question? Okay, a student draw light rays passing through lenses P, Q, R, and S. So this is lens P, this is lens Q, lens R, and lens S. Okay. F is the focal point of all these 4 lenses. So which drawing show the correct path of the light ray? So this is related to the rules of drawing ray diagram for convex and concave lens. So number 1, correct or not? Can you see the light ray? It is passing through the principal axis and continue travel at the principal axis. This one. Okay. Number 2, we have concave lens here. Okay, concave lens. So concave lens, the light travel parallel to the principal axis, and then it shows here it diverges out from the focal point. Okay, this one correct or not? Number 2, correct or not? Okay, this one follow rule number 2. Correct. Okay, ini pun betul. Betul kan? Okay. How about number 3? Students, number 3. Number 3 correct or not? We have a convex lens. Okay, we have convex lens. Okay, the light travel parallel to the principal axis and it is converge here. It shows it does not converge at the focal point. So this is wrong. Okay, this is wrong. Okay, and then number 4, correct or not? Betul ke salah ni? Number 4. Number 4, we have convex lens. Okay, we have convex lens. So where is the light travel at? The light is travel at the optical center, right? The light is travel at the optical center. So it will continue travel in a straight line. So this is follow the first rule. Okay, follow rule number 1. When the light passing through the optical center, it won't be refracted. Continue travel in a straight line. So this is correct. So which one is the correct answer? Number 1, number 2, and number 4. Okay, so answer is C. 1, 2, and 4 is correct. Okay, are you clear with question 3? Okay. Okay, so okay, very good. Okay, now let's check on the structure question. Okay, you are given diagram 4.1 and 4.2, both shows convex lenses. Okay, and they give you shows an object at 2 different distance. So you can see this is the distance of the object in the first diagram where u greater than 2f. Okay, while this one, okay, where is the object at? Okay, it is placed in between f and 2f. Okay, so u is between f and 2f. F less than u less than 2f. Okay. So the first question, state 2 common characteristics of the image formed in both diagrams. Students, this is our image, okay, in 5.1, and this is our image in 4.2. Okay, can you give 2 common characteristics of the image formed? It is, yes, both are real and inverted. Okay, this one real, form opposite side to the object, so it is real. This one also formed at the opposite side to the object, so it is real. And both are formed below the principal axis. Okay, the third characteristic is opposite. This one is diminished, this one is magnified. So dia nak yang sama, common. So you can write real and inverted. Okay, now question B. Observe both diagram, compare the object distance. So what can you say about the object distance in 5.1 and 4.2? Compare the object distance. Is the object distance the same, or which one is greater, which one is less than the other one? Okay, this is how we do comparison. So 4.1 greater than 4.2. Yes, very good. So 4.1 greater than 4.2. Okay, simple, senang saja. Okay, and then compare the image distance. Okay, compare the image distance. If you go back to the diagram, this is image distance B. Okay, this is image distance in 4.1. So you can see image distance in 4.1 is less than the image distance in 4.2. Okay, 4.1 less than 4.2. Size of the image, you can compare the size of the image. Okay, size of the image in 5.1 is smaller compared to the size of image in 4.2. So we write 4.1 less than 4.2. Okay, and according based on our answer, based on the comparison we made, we write the relationship. So this is the relationship you can write. State the relationship between object distance and image distance. Okay, so from the comparison we made earlier, you can find when the object distance increases, image distance decreases. Or you can write they are inversely proportional. Okay, and then second, they ask you to state the relationship between the object distance and size of image. So you find out from our comparison just now, when the object distance increases, what happens to the size of image? It is decreases. Okay, or you can say inversely proportional. Okay, very simple, right? Okay, do you have any question to ask so far? Okay. Any question to ask so far, students? No? Okay, let us go to the application question. They give you diagram 4.3. Actually, this one 4.3. Okay. It shows a magnifying glass, okay, with sunlight passing through it. A piece of paper is put under the magnifying glass. So the question is where the paper should be placed to obtain the strongest heat from the sun. Okay, any idea? This is a question on application or a keypad question. Where the paper should be placed to obtain the strongest heat from the sun. Okay, anyone? Tak letak kertas di mana? Okay, to obtain the strongest heat from the sun. So this is magnifying glass is made of convex or concave glass, students. Convex or concave lens, magnifying glass. Our magnifying glass is made of convex lens. Okay, if you draw from a side, this is the glass made of convex lens. Cikgu padam dulu. Okay, it is a convex lens. Okay, this is the axis. Okay, so the light from the sun, okay, travel parallel distance, right? So where will the sunlight refracted at? It will be refracted at the focal point. Okay, so it will be refracted at the mean the light will be concentrated here. The heat will be concentrated here. So this is where we should place our paper at. Okay, you should place your paper at the focal point of the magnifying glass. Okay, what is the reason? Because all parallel light from the sun will be focused on this point. Okay, the focal point of the magnifying glass. Okay, so this is how to answer this kind of question. So again, where to place the paper? To obtain the strongest heat, we place it at the focal point. Okay, why? All the parallel light will be focused on this point. Okay, how to know the focal point? You can measure or you can adjust the position of your paper, okay, until you get when the light concentrated at one spot, so you can hang it there. Okay, so it is a try and error thing. All right. Or else you can do the activity conducted earlier in activity 1. You can use this magnifying glass, okay, and then place it in a distant object. Then we do the activity just now to determine where is the focal length. Let's say you know the focal length is at, the focal point is 15 cm. The focal length is 15 cm. So we place the paper 15 cm away from the magnifying glass. Okay, so how to know? You do the activity earlier to determine the focal length of the magnifying glass. Or you just do a try and error. Okay, just adjust the position of the paper until you can find the light is spotted on one point. Okay. Okay, and this is another question related to lenses. Now they give you, if you look at this shape, okay, you must know already this is concave lens. Okay, this is concave lens, yes. So we place the object now in between F and 2F. Okay, so the first one, name the lens in this diagram. So it is concave lens. Okay, students. Okay, question B, they ask you to sketch a ray diagram of the object to show an image form. So 3 marks for the drawing. And then later, 1 mark they ask you to state 3 characteristics of the image form. Okay, so to draw the ray diagram, okay, you can apply 2 of the 3 rules. Okay, you can apply any 2 of the 3 rules. Okay, good morning, Junwei. So how to draw? So this is how we draw the ray diagram. Okay, so this is the first rule. A light from the object travel at the optical center, so it is not refracted. Continue travel in the first, okay, in the first light. Okay, this is the first rule. Okay, and we apply the second rule. Okay, this is the second rule. A light ray from the object travel parallel to the principal axis. So this is concave, remember? So it will be diverge. Okay, diverge from the focal point at the front. So this is the second rule. And this is the intersecting point, so where our image appear at. So you get first mark when you draw this line, this is your second mark, and third mark when you draw your image. Label it with image or I. Okay, just label it with I. So we know there is your image. Okay, so 3 marks for that. Ini mark number 3. Mark number 1, mark number 2, mark number 3. And don't forget the arrow as well. Okay, the arrow as well must be shown. Okay, then 3 marks for that. And then the 3 characteristics of the image. Yes, what is the 3 characteristics of the image form? So it is formed at the same side, so it is virtual. Form above, so it is upright, and it is smaller, so it is diminished. Or you just remember for concave lens, it is always virtual, always upright, always diminished. Okay, yes, simple. Okay, that goes with the position and characteristic for object image for concave and convex lens. Okay, students, this is the last part of 6.3, the fourth learning standard. Explain linear magnification. So this is the formula for linear magnification. M equal V over U. Okay, so what is linear magnification? Okay, for example, if you are using magnifying glass, okay, where we place the object at a distance less than the focal length, you can see that the image form is magnified. Okay, so how many times actually the image has been magnified, we can determine by calculating the ratio, okay, of the size of the object and the size of the image. Size here represent by the height, okay, the height of the image and the height of the object. Okay, so as you can read here in point number 2, the comparison between size of image and size of object can be expressed in terms of the ratio. So this is the ratio, okay, of the height of image to the height of object. So this will give you linear magnification. So what is linear magnification? It is the ratio, okay, the ratio of height of image to the height of object. Okay, so how to apply? Very simple. Okay, for example, this is the ray diagram showing when we place the object is here in between F and 2F. So this is the characteristic of, this is the image form. Okay, here we apply rule number 1, new rule number 1, and this is rule number 2. Okay, so you can see the image is H1, even H1 is the height of the image. H0 is the height of the object. U is the object distance, and V is the image distance. So students, to find linear magnification, this can be determined either from this, okay, the ratio of height of image to the height of object, and second, it is also can be determined from this one, the ratio of the image distance to the object distance. Okay, V over U. Okay, which means we can find magnification either by using the first ratio, height of image to the height of object, or by using the second formula. Okay, image distance divide object distance. Okay, and later when you count the value for M, if you find the value is less than 1, okay, if M is less than 1 means 0.1 to 0.99999. So it shows that the image is diminished. Okay. And when m is exactly 1, okay, when the ratio is exactly 1, it means that the image has the same size as the object. Okay. And later when you find out m is greater than 1, okay, greater than 1 means from 1.001 until a certain figure. So it means that the image has been magnified. Okay, the image has been magnified. Okay, very simple. Okay, how to find magnification? Height of image divide height of object, or image distance divide object distance. Okay, m less than 1, image diminish smaller. Equal to 1, same size. Greater than 1, image is bigger than the object, or magnified. Okay, let us try to do this linear magnification in this question. A very simple question. Okay, you are given an object with a height 5 cm. Okay, place 20 cm from a convex lens. Okay, and later a sharp image is formed on the screen, which is 40 centimeter away from the convex lens. So the question is, what is the height of the image, student? So we are looking for height of image. So how to find height? So what are you given here? Object with the height 5 cm. So this is h naught. Okay, 20 cm, this is what? 20 cm from a convex lens. This is object distance. Okay, and then an image formed on the screen 40 centimeter from the convex lens. So this is our V, object distance. Okay, so how to find HI when you're given H naught, U, and V? Okay, any idea? So you are given with this, how to find HI, height of image, so we can use this. Okay, height of image, this is from the linear magnification. Height of image divide height of object equal to image distance divide object distance. Okay, and you will find HI will be 10 centimeter. So it will be 10 centimeter. So height of image 10 centimeter. Height of object is 5. So you can see that the image is bigger than the object. All right. Okay, then second question. Okay, try to find. The second question is about a similar with number 1. They give you again convex lens as shown in the diagram. You are given with several distance here. 8 centimeter. This is 26 centimeter. Our object is 2 centimeter of height. And this is where our image is at. The question asks you to find what is the height of this image. Okay, can you try to do this? 2 centimeter is HO. Can you tell me what is our object distance, students? What is our object distance as shown in this diagram? Where is our object distance? This is our object distance. This is U. Okay, so U is 8 centimeter. Okay, U is 8 centimeter. What is our image distance? This is image distance. Okay, so what is image distance? Okay, what is the image distance? Can someone type there? What is the image distance be? The distance from the object to the image is 26. So to find B, 26 minus 8. Yes, so it will give you 26 minus 8 berapa? Okay, this one. Okay, it is, this is B, how to find. So B is 18. Okay, 18 centimeter. Okay, I erase first all the marks I have made there. Okay, so again, we apply the same formula. Height of image divide height of object equal to image distance divide object distance. So we are looking for HI. So this is 2 cm, the object height, and 18 centimeter. This one is the image distance. Okay, 26 minus 8. 18. Okay, and VU is 8 centimeter object distance. So by this, the height of image is 4.5 centimeter. Okay, very simple, 4.5 centimeter. Okay, okay. So we have done with 6.3.4 to use linear magnification in order to determine either the object has been diminished, magnified, or the same size as the object. Okay, this one is an addition. Addition notes mean it is not inside your textbook. Okay, so it is an addition information. So the first one, what is the power of lens? So for those who are wearing spectacles, normally people ask, what is the power of your lens? 500. Ada yang 1000 power. So what is this power of lens refers to? Okay, power is refers to the ability of the lens to bend light entering it. Okay, so power shows you the ability of the lens to bend light entering it, and we measure power in a unit of diopter. Okay, in a unit of diopter. Yeah, Ong Zheng, what is it? We measure power in a unit of diopter. Ini bukan maths, bukan derivation di WDT, right? Okay. For example, this is how to find a power for convex lens. Okay. If you look at these two lenses, they are different in thickness. Okay. This is a thin convex lens. On the left is a thin convex lens. On the right is a thick convex lens. Okay. And you can see that this is the angle of refraction. Okay, angle of refraction for thin lens, and this is the angle of refraction for thick lens, theta 1 and theta 2. And you can see here for a thicker convex lens, okay, for a thicker convex lens, the power of lens is higher. Okay, the power of lens is higher and will converge light ray at the bigger angle. Okay, remember just now power means ability of the lens to bend light. Mean here for thicker lens, okay, the light bend at the greater angle of theta 2. So it has a power, higher power compared to a thinner convex lens. Okay, theta 2 greater than theta 1. Okay, well this one, okay, what is the differences between thin and thick convex lens? So from here we understand that the thicker the center, the shorter its focal length. Okay, this one. Okay, this is the focal length of a thin convex lens, and this is the focal length of a thick convex lens. And you can see clearly from that, a thicker convex lens has a shorter focal length, but a high power. Okay, a high power. So we can say that power of lens inversely proportional to the focal length. Okay, power is inversely proportional to the focal length. Okay, and for concave convex lens, the power and the focal length is taken as positive value. Okay, and this is the formula to determine power. So power is the reciprocal of focal length. Power is 1 over F, where F ini is in a unit of meter. Okay, so you will find power in a unit of diopter. Okay, remember power is inversely proportional to the focal length. And thick convex lens has a higher power and shorter focal length. Okay. This is for concave lens. Okay, concave lens. Again, we have thin convex concave lens on the left, and we have a thicker concave lens on the right. Okay, now for concave lens, it is the opposite. Okay, for concave lens, you will find out, okay, the angle of refraction, okay, for concave lens is greater, for thinner. Okay, theta 1 is greater than theta 2. So we say for concave lens, the higher power lens will diverge light ray at the bigger angle. So it means for a thinner concave lens, it has a high power compared to a thicker concave lens. Okay, as mentioned here, the thinner the center, the shorter the focal length, and the higher the power of the lens. Okay, and students, for concave lens, the power and focal length is taken as negative. Okay, negative shows, negative ini dia bukan, it's not a magnitude. Negative, positive only show you the difference between concave and convex. So when power and focal length is positive, we know the lens is a convex lens. When the power and focal length is negative, we know the lens is concave lens. Okay. Okay. For example, we take a look at this question. Okay, you are given focal length of a convex lens. It is 20 cm. Okay, so find the power of the lenses. Okay, find the power now, student. Very simple. Okay, from the formula of P equal 1 over F. So what is the power of this lens? Okay, can you calculate? So this is the formula to find power. It is the reciprocal of the focal length. But you have to remember F ini must be in a unit of meter. Okay. So how to find the power? So it is 1 over positive 0.2 meter. 20 cm is 0.2 meter. So the power is positive 5 diopter. Okay, positive 5 diopter. Okay, this one, second question. Now you are given concave lens. Okay, given the focal length is 10 cm. So what is the power of the lens, students? Again, we apply the same formula. P equal 1 over F, where F must be in meter. And for concave, the focal length is negative. So 10 centimeter is equal to 0.1 meter, which means the power is negative 10 diopter. Okay. Again, the negative and positive sign shows to you that positive is for convex and negative sign is for, yes, must write positive and negative. Okay, to differentiate convex and concave lens. Okay. Okay, this is the question related to the magnification, power, and focal length. Okay, we try to look a bit. Okay, this is SPM past year question. Okay, first one, student. You are given diagram 5.1 and 5.2. Both are using convex lens. Here you can see they are of a different thickness. Okay. The first question, state the light phenomenon involved to produce image of the convex lens. So what is the light phenomenon involved here? Light phenomenon involved to produce image of convex lens. So lenses operated based on what? What phenomenon? Is it reflection, refraction, diffraction, interference? So which one the phenomenon applies in lenses? It is refraction. Okay, refraction of light. Okay, now observe both diagrams. Compare the thickness of the lens. So how can you compare the thickness? Okay, look at the thickness. 5.1 and 5.2. Which one is thinner? Which one is thicker? Okay, so you can say thickness 5.1 greater. Okay, 5.1 greater than 5.2. Or you can say 5.1 is thicker than 5.2. Okay, then compare the focal length. Okay, where is the focal length of the lens? Okay, this is the focal length. Okay, this is F and this is F. Okay, just now we understand for thicker lenses, it has a shorter focal length. Okay, for thinner convex lens, it has a greater or longer focal length. So you can write 5.1 less than 5.2. Okay, or focal length in 5.1 is shorter than 5.2. Then compare the height of the image. Okay, this one you compare the height of the image. So it is obviously that H2 is greater than H1. So you can say image in diagram 5.2 greater than 5.1 or the other way around. 5.1 less than 5.2. Okay. Second, okay, based on your answer, relate the thickness and the focal length. Okay, as we learned before, as we discussed just now, inversely proportional. When the thickness is higher, the focal length is shorter. Okay, when the lenses is thicker, the focal length is shorter. So it is inversely proportional. And now relate focal length with the height of image. So you can see from the previous comparison, they are directly proportional. Okay, when the focal length is longer, image is bigger. Okay, okay, now these students, a leaf blown by a strong wind cover the upper portion of the convex lens in diagram 5.1. Okay, what will happen to the size and brightness of image? Okay, do you understand this question? Okay, just now sini ada daun tebang. There's a leaf fall and cover this part, the part of your camera or your lens. So what will happen to the image form? Any changes on the size or any changes on the brightness? What will happen? This is K-Bat question. Okay, a leaf blown is strong wind cover the upper portion of the convex lens. So what will happen to the size and brightness? So is it the size going to change? Logically, no changes, right? Because no changes on the image, no changes on the object distance. Okay, so we write size unchanged, but the brightness will be decreases. Dark sikit, yes, the brightness decreases. So we say the brightness decreases, but no changes on the size. Okay, it's true, Sinwei. Okay, now question number 8. Okay, question number 8. Okay, this is SPM 2009 question, and it is also a question in your formative practice 6.3 in your textbook, page 258. You are given diagram 8.1 shows an image seen through a lens. This is the lens. This is a checkerboard. Okay, we place a lens and you can see that the checkerboard appear to be bigger, right? Appear to be magnified. Okay, the first question, name the light phenomenon involved. Students, what is the light phenomenon involved here? Again, it is refraction. Okay, refraction of light. Okay, and then second, draw the ray diagram to show how the image in 8.1 is formed. So what do you think the position of the object here? So actually this one is application for magnifying glass. Okay, if you unnoticed, this is magnification of magnifying glass. So we place the object less than the focal length. Okay, and this will be the characteristic of image form. Okay. Okay, this one. So this is how we draw the ray diagram. And the next question here, the focal length of the lens in diagram 8.2 is F. Okay, they give you the focal length is F. And referring to F, suggest a suitable position to place the object to produce an inverted image. So this one you have to remember. Okay, for a convex lens, in which position it will produce an inverted image. So inverted, it must be real. Okay, real mean form at this side. So to produce a real or inverted image, you must be greater than F. Means our object must be placed, okay, after the focal point, somewhere here at the after the focal point. Then the object will appear at the opposite side where it will be inverted point and real. Okay, this one you have to remember the characteristic of a position of a convex lenses. Okay, so I guess that's all for 6.3 image formation for lenses. Okay, do you have anything to ask? Ada apa nak tanya tak? Macam no. So, are you clear with our discussion today?